Thank you very much. My name is Caroline Edelstam, and I'm the Secretary General of Engineers Without Borders in Sweden. First of all, I would like to welcome you all to our Sustainable Engineering Week 2025. I'm happy to see so many people joining us from around the world. Today, we are here to talk about how we're going to eliminate 4% of Sweden's CO2 emissions. And with us today, we have Mikael Kullman, who is the project manager at Heidelberg Materials, and who's going to talk about how the Slite, situated in Gotland in Sweden, CCS program is one of Sweden's largest transformation projects. And we're going to discover how this initiative will contribute to a climate neutral society. And by 2030, it aims to produce cement with net zero carbon dioxide emissions, ultimately striving for negative emissions. And this is a unique project in Sweden, and it's also a unique project within the field of cement. And using innovative CCS, carbon capture and storage technology, emissions will be captured, transported, and safely stored, and will add to reduce Sweden's total carbon dioxide emissions by 4%. So now we will learn how it is to, this is a leading project and why Heidelberg is actually committing to this project and how it contributes to building a climate neutral society at large. So I would like to welcome Mikael. Please, I leave the floor to you.
Thank you very much, Caroline. It's a true pleasure to have the opportunity to speak in front of you, and I'm happy that we have people from all over the world. As I assume that it's Engineer Without Borders, we have a few engineers here. I'm an engineer myself from Chalmers University. So I will be a bit technical, but not fairly shallow. So I hope that I will at least meet some of you in terms of questions when it comes to technical details. Regarding the project that Caroline was talking about, but also the background and also in terms of the future plans, etc. So let's see here. There it is, yes. Oh. So the heading of my presentation is how to eliminate 4% of Swedish CO2 emissions, but that is not the only truth, actually. I will also present, I would say, more details about what CCS is all about. That is because some of you may know about it and some of you may not. So I will go through, again, as I said, a bit shallow, but still speak about different technologies and different opportunities. Of course, I will also talk about why it's required within the cement industry and how we will do that. And then I will do more practically in the sense of the projects that we are talking about. Slite, of course, in Sweden, but also a sister project in Brevik in Norway, which is also working at the same path, but are a bit earlier in the process, actually will commission their plant already during 2025. But I'll come back to that. But this is the overall content of my presentation. But before I do that, what is Heidelberg Materials? Some of you may have heard about the company, some of you not, so I will give you a short introduction. Heidelberg Materials is a global company, so we are active all over the world with, more than 50,000 employees and more than 3,000 locations all over the world. And what are we actually then doing? What is the whole thing? Is that we are producing aggregates and precast concrete and ready-mix concrete. But the basic major product that is of importance is the cement production. And all the activities that we are undertaking in different plants all over the world, totally we have a capacity of producing 170 megaton of cement, which then, of course, in the end of the day, will become concrete, which you will see everywhere in the surrounding society. Any infrastructure, I would say, contains some kind of concrete, which is a mix of aggregates and cement, and that is what we are producing at Heidelberg Materials. So, as I said, we are working all over the world, but when it comes to Northern Europe, which is the area which I belong to, We are having activities in Norway, Sweden, and Denmark, the Scandinavian countries, including Iceland, but also the Baltic states. And when it comes to cement production, we have 4 production plants, 2 in Sweden and 2 in Norway. And totally, it's a total capacity, cement production capacity of more than 4.5 million tons per year. But in the future, my presentation here, I will actually focus on 2 locations. One is in the Baltic Sea, which is the Slite one on the island of Gotland, that is Sweden. And then it's also in Norway, in Brevik, which is about 150 km south of the capital of Oslo. That is the other production site, where we are then working with these CCS activities, which I will come back to later. So that was very briefly about Heidelberg Materials. But what about the transition of the cement industry? Why is that required, and how would we do it? So first of all, when it comes to cement, how do we actually produce it? That is fairly important in the sense of why it's important for us to transform into a more climate neutral perspective, is that the core raw material for producing cement is limestone. That is the more than 75% of the cement in the end contains of limestone raw material. What we do with the limestone is that we crush it, we take it through a raw mill and grind it through a raw mill before we enter into the actual production, where we under high heat we go through a calcination process where the limestone actually enters into what we refer to as the clinker, which is the base material for later cement production. So we go through into the calcination in the cyclone tower, as you see here in the middle, and then up to the right, we're sintering it into the kilns and then cool it down before we take the clinker, as we now call it, grinding it in the cement mill and also add some aggregates to make the actual cement and the quality that we are looking for before we store it in the cement silos prior to our further transportation to our clients. When we are calcine this in the cyclone tower and under much heat, of course we had a lot of energy to do this, a lot of heat, and we also then get a lot of emissions, and that is treated and then we emit it to the air. We also get a lot of energy, excess energy, that we produce power and also district heating. So that is also a part of the whole cycle. But we have a problem with cement production, and that is actually that the cement production contributes to worldwide more than 5% of the total global carbon dioxide emissions, and that is of chemical reasons. That is, of course, we have it from the fuels, as any combined heat and power plant has, or whatever, when you combust some kind of fuel. But more than 60% of the carbon dioxide emissions from the cement production actually comes from the limestone. When we heat up and produce the clinker, the limestone is actually releasing its carbon dioxide to produce the clinker and the calcium oxide, which is the cement-based product. And the carbon dioxide in itself then will then be released if we don't do anything about it. Well, we can do different things, and that is, of course, to reduce the fossil fuels. That is one way of reducing the carbon dioxide. We can also add some further cementitious materials into the cement mix, like we could use, for example, fly ash. We can use slag from the iron ore industry, etc. But in the end of the day, we still need limestone, a quite significant share of limestone, and thereby we cannot avoid the generation of carbon dioxide in our production. So what do we do then? After we have done all this, apart from that, we then need to introduce, as you see here also, we have to introduce some kind of capture system for the carbon capture. So we add that into the emission and the stack or chimney where the emissions previously has been released. And then we capture it and we compress it and liquefy it and store it until we can transfer it to the next station, so to say, for storage. Now we come back to the technologies, how we do this in a while. And now it has been mentioned Slite in Sweden. I also mentioned Breivik in Norway. But actually, Heidelberg Materials, we are working with this all over the world. Although the two projects that I will present more in detail later, they are the front runners. But when it comes to all, I would say all Western Europe and also Northern America, we have more than 10 projects currently planning for different kinds of carbon capture and storage activities. Different sizes and different capacities, but for sure the target is there for the whole company or for the whole group to introduce this technology with the aim of prior to 2030 capture totally 10 megaton, but what is even more important that beyond 2040 and 2045 the whole group aiming for to be carbon neutral by introducing carbon capture systems in different ways. So before we go into the technology that we are applying and also how it will look like in the specific sites in Slite and Breivik, I would like just to have a short intro to the situation in terms of what is CCS, how do we do this, and what is actually entailed. And this is what you see in front of you right now is a kind of a regular carbon capture value chain, exemplified by the Nordic way of doing it. And if you take it from the left to the right, we have in this case a cement manufacturing activity or site where we're then introducing a carbon capture facility. In this case, it says amine based, but I will also come back to the different technologies that you could use in that sense. When we have captured it, we prepare it for transportation by liquefying it because that's required in order for gaseous is too voluminous. So we have to have another form before we transport it. And that we do by compressing it and very low temperature. So we can transport it either by ship or vessels over the sea to some kind of receiving terminal, or by pipeline if there is if the infrastructure is efficient enough to do that. So, but that could be different depending on the different locations. From the receiving terminal, then it's further transported for injection to final storage wells, which often is, especially in the Nordic countries, are focusing more on the bottom of the sea, and then another 4,000 meters beyond the bottom of the sea for further injection. And I will then, in my continuous presentation, go more into the actual carbon capture technology on the left side, and then also make presentation more of how is it actually done and the conditions for the final storage and the geological situation that is required for that. But if I start with the carbon capture itself, there are different principles when it comes to carbon capture. And if you take it generally, either you can go for what we refer to as pre-combustion, and from that you could actually hear what it's all about. That is that you capture the carbon dioxide before you make any form of combustion of a fuel or similar. And the technology here, which is fairly low technical readiness level at this time, is that you first gasify the fuels, thereby in that process you capture the carbon dioxide, and after that you combust the gas that you have produced, and thereby it's very easy actually to avoid any leakage of carbon dioxide from the process itself. But again, that kind of pre-combustion activity has to be undertaken and also implemented on a green project perspective, that a greenfield project. Thereby you have to introduce the technology already from the beginning when you build a plant or similar. That is often not the case, especially not now, and especially not in the cement industry, where the cement production facilities are already in place. So for that kind of activity, I would rather say that we have the other part, which is post-combustion, which is then we are having some kind of combustion of a fuel or similar, and then you get the fumes, and then you capture the carbon dioxide after that. That is, I would say, the most developed technology as of today, and most of the project that we are looking into is actually post-combustion perspective. Additionally, you can also actually add technology where you you still have post-combustion, but you add oxygen before you actually make the combustion, and thereby it's a lot of oxygen, and then it's much easier to capture the carbon dioxide. But again, that technology is also related to a specific case where you do it in a greenfield project. What I mean there is that you introduce it when you build the actual production site in order to accommodate this kind of technology. So what does this then mean if we take the post-combustion and a regular way of acting, so to say? And this is also a flow chart where you go from the left to the right. We have the flue gases coming in from the left, from the some kind of production. In this case, our case is a cement production facility. You cool down the flue gases, and then you clean it also to prepare it for the actual amine process that is coming later. The cleaned and cooled flue gases go into an absorber, which is the place where you take an amine solvent and, in a scrubber perspective, sprinkle the amine solvent over the fumes or the emissions, and the amine solvent then connects to the carbon dioxide and bind the carbon dioxide, and then trickles down to the bottom of the absorber, and the rest of the emissions goes out in the top and then are released as emissions. The captured carbon dioxide with the amine solvent is then transferred to the next phase, which is the desorber. And in the desorber, you heat it up, this amine and carbon dioxide solvent, and thereby, by the heating, then the carbon dioxide is then released from the amine solvent. The amine solvent is going in the bottom of the desorber, and the clean carbon dioxide is then transferred to the top of the desorber, and it can then be transported further for the compression and liquefaction process. And that's where you then make it the carbon dioxide fluent by 15 bars and up to -30 degrees before it's intermediate storage, before you then can transfer it to a ship or a vessel or pipeline, with that matter, for the final storage later on. So that is the technology as a sort of an overall principle. I have said now for the amine, but I would say that the similar technology used for different kinds of solvent and different kind of technologies that are developed. This is the overall principle for all of them, I would say. Okay. Then we go for the next part, and that is on the sort of right side of this the value chain. That is the geological storage. We have now transported the floating carbon dioxide to some kind of site where we will inject the carbon dioxide for final storage. And what are the conditions for the final storage? Well, that is geological formations that sort of undertake and have some certain conditions. And one of them is that you have a structural storage, and that is that you have a seal where you inject the carbon dioxide under a cap. And this cap is, as I said before, 2,000 to 3,000 meters beyond the surface, or below the surface, sorry. And that's a cap of impermeable geological formation that doesn't let the carbon dioxide release upwards. So it's of a very hard rock that is not geological formation that has been developed through the years. Under this seal, what we also would like to have and also look for is saline aquifers, and that is number 2 here, where the carbon dioxide is go through a enter into a solution with the saline aquifer, and thereby the carbon dioxide together with the salt having a heavier density goes to the bottom to the saline aquifer. So thereby you have another way of capturing, or sorry, storing the carbon dioxide. The third part is actually that in this area, what you also would like to have is formations, geological formations that are more porous. And in the pores of these geological formations, the carbon dioxide then goes into these pores and also stay there. That is the third part of the storage itself. And then eventually we also have mineralization, where the stored carbon dioxide after hundreds and thousands of years actually from geochemical reactions turn into stable carbonates, and thereby in the end of the day gets to be a part of the geological formation and become a part of the stone itself. So these are the four principles. But as I said before, the best way, the optimal condition, is that you actually have everything at one place. So this is when you look for these kind of geological formations, where to store the carbon dioxide. This is what you look for, a combination where you have a cap, you have the aquifer, the porous materials, and then also availability of hard rocks. That means that you also in the end can have a mineralization. So that is the total optimal situation that you are looking for. But this is, as I said before, as an example, available at many places in the North Sea. But if you come to this storage, there is quite a few, often you have some questions about this, actually doubting that, will this actually work? Will it not leak out? And that is a good question. How do we know that stored carbon dioxide is not leaking out? But one could say that we know that because this is not actually a very new technology. We've done it for many years. It has been used as a part also in order to, when they are extracting oil and gas from the oil and gas fields, carbon dioxide has been used, injection of carbon dioxide has been used also to sort of make the extraction of oil and gas more efficient. And then you can see that the carbon dioxide actually stayed in the gas wells, etc. So more than 300 million tons has actually been injected in that way, and thorough investigations afterwards show that the carbon dioxide remains in these caverns down below the surface. We can also say that actually oil and gas from the beginning has been generated these kinds of geological formations, and as we know, that stayed there for quite some time until we had to sort of suck it up or excavate it. So we believe that definitely the carbon dioxide, it will remain in these caverns for a long time, for eternity actually. But still, of course, we need to do very, very thorough investigations, both when we find the places, but also when we then finally utilize and start the injection. So we need to do a lot of seismical studies, pressure measurements, chemical analysis, and also, of course, monitoring to ensure and measuring around the area so that you don't see, so that you see once carbon dioxide eventually would come out in any places. And if that happens, you can mitigate that by also stopping the leakage and then, or close the whole the well as such and start drilling at another place. But the experience shows that this will not be the case. How much can then be stored in total? And that is, of course, also a very good question. Is there a limitation? And one could definitely say that the knowledge about the geological formations all over the world, it's for sure that the limitations is not in storage areas. It will definitely be in how we generate or actually how much we can capture. So in any country, almost any country in the world, there will be, following very detailed analysis, these kinds of storage areas will definitely be found. So that is not a limitation. And thereby the question that is come up often in Sweden. Why don't we store in Sweden? Is there a possibility to store there? And definitely there is. However, the investigations and knowledge about geological formation is not as good as, for example, in Norway. Currently, studies are undertaking in south of Gotland, but also south of Sweden, with promising results for sure. But we believe that it will take at least 15 up to 20 years before we have commercial activities in this case, also for Sweden, so we can store our own carbon dioxide, so to say. So from Heidelberg Materials perspective, we foresee that our carbon dioxide that we capture will be further captured in Norway or potentially also Denmark, and I'll come back to that. I hope now that yes, I changed the picture. So now, more practically, what do we actually do? And I will show you two projects, and that is the timeline we have in front of us. The first one is the ones in Breivik that I mentioned that will be in operation now 2025. I will present that a while, and then also go into depth with what the heading of this presentation was all about as well. That is in Slite, what we will do there in terms of also reducing the carbon dioxide emissions in Sweden with 4%. But first of all, Breivik. It's soon to be commissioned, and here's a picture of the site itself. And the plant in Breivik, they produce about 1.2 million tons of cement every year. And what will happen there is that when commissioned, we will capture more than 400,000 tons of carbon dioxide per year, which actually represents about 50% of the total emissions that are currently emitted from the plant. This is also part of a Norwegian government project, which is called a Longship project or Longship project, where other actors are actually playing in terms of the storage and transportation and storage facility. And this is a picture of the Longship project, where you have, apart from Breivik and Heidelberg Material Breivik, you also have a plant in Oslo and also one in Belgium, Jarab, which is then all three are then transporting their carbon dioxide to Northern Lights, which is called the company called, for in their receiving terminal for further injection in the North Sea after that totally. So again, I said that we are starting in 25, and I will show you some picture of what's happening here. This was already in August 23. Here you have the absorber that I mentioned to you before. This one is about 60 meters long, and it's produced in one piece and then transported to the site, and there you see it's lifted up. You also see here in mid 2024 the last heavy lift. And why do we have heavy lift? That is because while we're introducing the carbon dioxide or the carbon capture activities, the cement plant has to be running at the same time. So thereby most of the equipment is actually produced in a modularized system in other places and then transported to the site and then lifted and installed during short shutdowns when these parts can be implemented. So, and the final picture here is actually in December 24. It's a bit tricky to see here, but that when we had mechanical completion, you see the shining part is a new part, and then you also see in the back here, you also see the sorry, you see the absorber and the chimney of itself also on top of that one. And then also in the harbor at the same place, we have the intermediate storage. These are 6 tanks of about 800 cubic meters each. They're quite big, as you see, but then that's where it's intermediate stored. And then further Northern Lights, as I mentioned before, which is a company for transportation and storage. These are the ships that will come to the site for and loaded with the floating carbon dioxide, and then transported to Northern Lights receiving terminal in the mid of Norway, which is called Øygarden. And from here, then it's injected by a pipeline. You see the sea here in the top, in the fjord. It's about 15 kilometers out where you have the actual injection to the final storage activity underneath the bottom. So this is actually happening right now, and again in June there will be full operation of this. But what will you then do in Slite? What is the difference from Brevik, and what are the plans? And in Slite, this is a picture of the site itself, and here you see, which is very important when you have a cement facility, is that you also have the limestone quarry in close relationship to the actual production site to make it more efficient. And in Slite case, as same as Brevik, we also have a harbor close to the, directly close to the cement production site. Again, what are the Slite CCS project all about then? I mentioned Brevik, that was about 400,000 tons, but in Slite we will capture more than 1.8 million tons of carbon dioxide every year. And the major difference here with Slite is that we will capture as much as possible. We aim for more than 95% of the carbon dioxide that is today is emitted, tomorrow will be captured and further stored. And thereby we need to also introduce a lot of new activities when it comes to heat recovery units, when it comes to energy generation, etc. But still it will be electrified to full extent. But in terms of size, it's unprecedented in terms of similarities in the cement industry. So this is the largest cement industry carbon capture project that is actually currently in planning. And as I said before, when we have introduced this plant in 2030, we will capture the carbon dioxide and transport it by vessels to some kind of location in the Northern Sea, exactly where it's still under assessment. But as I said, 4% of Sweden's total emissions is quite significant step forward for sure. And this will happen in 2030, and we are currently in the plan, following the plan. So you see here 24 to 26. We are initiating the detailed planning and design phase. We are currently preparing procurement of the major contractors to prepare this detailed design, and then also entering into the construction and installation. We haven't taken the final investment decision yet because we need to know certain details. For example, how much will this actually cost? And it will cost more than 1 billion euros, we know for sure, but still we need to understand how the financial sustainability of the project, etc., will look like. But also technical details we need to know. We need to know more also about the permitting aspect, etc., that we're working with right now. So a lot of intensive activities are ongoing currently for sure. But the plans for 2030 has been there for many years, and we are still keeping up with that timeline. So what will it actually look like in terms of infrastructure? And here's a picture of the site from another angle that you saw before. You see the sea and the harbor beyond the facility. You see the chimney, now it's smoke coming out, and that is where carbon dioxide today are emitted. And you also see on the left side of this picture, you see the former quarry, which is underneath these oil cisterns that you see there. And that is also a very important area, which you will see in the next picture. This is an illustration how we think it will look like in the future. You saw this chimney before, now the chimney is taken away, and instead you have a green pipeline where you first take it to a certain place for treating the flue gases, and then down to what we call the old quarry, the eastern quarry, where you have all the carbon capture facilities with capture, compression unit, and liquefaction. And also in the left corner, you also have the intermediate storage for the captured carbon dioxide. And then in the end, you have the pipeline for the harbor, and you also see the vessel and the harbor in the water. And here you have from another angle a new pier, and we also have to extend the whole harbor to allow for these larger vessels to accommodate an efficient transportation of the carbon dioxide. So this is what will happen in the future. Again, this is an illustration, but we believe that it will actually look like this also in the future. So because we are coming quite far in our planning. And again, finally, what will happen? And as I said before, the carbon dioxide storage, we are looking in different alternatives. We may use the same as Breivik, but there are also other alternatives, both in Norway and Denmark, and even onshore Denmark are possibilities that are now coming up as a very, very interesting opportunity. That is actually what I was thinking to present to you. We have a website for the project, and you are much welcome, of course, to visit that one. It's both in Swedish and English. It's Slite CCS.se, so have a look there. And of course, if you want any more information or interested, just give us a contact, or me that working with it, over phone or email. And I trust I haven't sort of added that here, but it is also visible on the website Slite CCS, where you have contact persons, etc., for your information. So
Thank you.
now it's happening for real. So this is the future. Thank you very much.
Thank you so much, Mikael. Fantastic to learn a little bit about this incredible project. I see that we have received some questions here in the chat. Would you mind, could you bring it up, Karin?
It's Gus Badran who's asking, hi, what is the CO2 concentration of the flue gas and how much will you be able to remove? What is estimated cost and energy requirements, percentage weighting of CO2 capture versus transport versus storage? I feel that that's quite complicated questions, and there's not one, it's more than three or something. But could you just kind of touch on the subject?
First of all, when the carbon dioxide content in the flue gas itself, it varies, of course. You want them to be as high as possible, but we currently are designing it for, it's about 11 to 13%. So that is the base that we are working from, so to say. But again, as I mentioned before, that the technology with adding oxygen in this combustion technology, then that is actually to increase also the carbon dioxide content, because of course it's much easier then. We will collect 95% of that. That is the aim through this technology. And that is also energy consuming, as is also a question. So there is a lot of, in our case, we use a lot of electricity to increase the capacity, but also, of course, introducing heat recovery systems also from the system itself. But we believe that in the range of 400 kilowatt hours per ton of carbon dioxide is used for the capture process itself during operation.
I have another question here that was a bit early, so maybe you have already explained, but it's Todd Flack who wants to know what's the fuel mix for this cement facility?
Very good question. And that varies, of course, very much between different sites, and that may be there that's where the question comes from. As you have very high temperatures in the kilns, you need certain heat values of the fuels. So we try to, as much as possible, introduce bioshare. And our aim is by 2030 to have more than 50% bioshare in our fuels. And that is because we need some of the fossil fuels, the coal, which we try to exchange through biocoal. And we also have what is called RDF, residual derived fuels, which is actually waste. That is a mix of biofuels as well as fossil fuels. So, but in the end, hopefully we can increase the biofuel more and more. And the first step, as I said, to 2030 is 50%.
We have a question from Gus Badran. You mentioned capture capacity. What is storage capacity?
I think that I'm not really sure if I understand the question, but hopefully, capture capacity is what we have then 95%, and for Slite about 1.8 tons. And we're of course looking for storage capacity that meets that demands. When it comes to the total storage capacity in the Northern Sea, it's tremendous. For example, the Northern Lights that I mentioned, that is only one project, and one of the first projects, they have a storage capacity of about 8 to 9 million tons per year. So that covers a lot, but there are many projects in that range developed today in the North Sea. And as I said before, new projects are coming up in Denmark. We also foresee that, for example, in 15 or 20 years, the Baltic Sea may also be host, so to say, for carbon capture, for carbon storage as well.
Thank you. And one more question from Todd Flack. When is your final investment decision for Slite CCS?
That is a very good question and also a tricky question. We are aiming for, I would say, third quarter 26. But before we enter there, as I said, we need to have the financial understanding, financial sustainability in place. We need to know the total costs, but we also need to have the plant permit in place, which we are now applying for, because that is required when we're entering this new technology.
I must say it's very impressive to hear about your cement production and with the net zero carbon dioxide emissions. I was just one final question here, wondering if how do you think this will affect and inspire other industries in Sweden, but also globally?
Hopefully, this is sort of something that this technology, I think, is required. I mean, this is not the solution. It has to be added. I mean, this is sort of the last resort, so to say. But definitely, there are so many industries that perhaps we don't have any other ways of moving. And if we can show that this is possible, not only technical, but also from a financial and operational point of view, that is a great asset. And I would say that from an innovation perspective, we are working closely together with, of course, with our sister companies, but also within the industry, cement industry, but also cross-border into other technologies in other industries to disseminate our findings and results, but also to help each other, because that is very important. For example, there is what is referred to as the European Commission has an innovation fund where you can support these kind of projects. And there is a very important feature when you're applying for this is actually the scalability and replicability aspects and potentials. And that's where we have found that we have really good potentials there, because similarities, there are many projects and many situations with similarities to our situation. Who can learn from our project?
So Sweden will become a leading star in negative emissions then, finally.
Hopefully we will be one of the definitely a front runner, and we are already today, I would say. But other countries are coming quick, so it's a race, but we all are benefiting from it for sure.
Thank you so much, Mikael. It's been a great honor to have our valued corporate partner, Heidelberg Materials, here with us during our Sustainable Engineering Week. I hope all of you consider to join our other events. We have 2 more this afternoon and 1 tomorrow morning. And very interesting to learn more about your project at Slite, Mikael. Thank you so much for taking your time, and thank you to everyone in the audience for being here with us today. Thank you so much.
Thank you, everyone.
Thanks.